first part. It got cut off unforeseen, unprovoked, because the memory card ran out. So I was listing the ways you can calculate power in different numerical situations in GCSE, A level, post 16, and undergraduate physics, and even postgraduate, if I may say so. So the first way you'll calculate it is power equals energy over time, so that's joules per second, like the original units, joules per second, which is known as watts, kilowatts, megawatts, gigawatts, and then followed by the second method, which shall be force times times divided by time. That again comes out to be joules per second. All of these end up as watts, i.e. joules per second. So the third one is a derivative, a substituted derivative of number 2. So this is force times velocity, used heavily in mechanics pertaining to objects in motion. And this one is mostly used for mg sine theta or mg cos theta divided by time, for times x divided by time, for objects at angular inclined motion. So this one, number 4, is slightly interesting because it pertains to, as I said earlier, to wave motion and EM wave motion, and that'll be the irradiated intensity per unit intensity times unit area would be the unit the power luminosity power for the unit area. Now moving on to the 5th and the 6th type and the 7th type that I should have marked as 7th. These 3 pertain to electricity, eddy currents, electromagnetism, circuitry, electric circuits. Now these aren't exactly the way you calculate power for electric circuits, but rather this is the quantization of heating, of how much heating has taken place in a circuit, which is made evident as power. There are other sinusoidal formulae for power, an RMS, root mean square speed, root mean squared formulae for power. That's under root power over under root 2 and half times p, and we're not going to, that's an AC theory, so enough of that. We'll tackle it when time comes, but the straightforward aggregation list of formulae that can be used to calculate power is this. So number 5 is current times voltage in a circuit. Not the small resistance voltage, not the EMF, but rather the major voltage, the battery or the DC voltage, or the supplied voltage, or the AC voltage, which will be 2 pi f over 1 over 2 pi f c. So that will be resistance 1 over 2 pi f c. So and then we'll have P time equals square of the current in the circuit times resistance evaluated for the resistor. So resistor times I squared times R. The last one is voltage squared divided by resistance. And these 3 are valid for ohmic metals, ohmic circuits. So it will not be valid for semiconductors, superconducting magnets, and the like. So what I'm trying to say is power is the rate of energy consumption, or the dot product of a radiated intensity per unit area, and it's used these formulae that I've just listed here will be used in electric, electronic, and thermal physics calculational analysis. Now by electronic I mean Hall effect with a bit of electromagnetism, but they will not be used, as I just mentioned, for superconducting circuits and semiconductor circuits, PNP, NPN, and diodes. So these formulae will not be relevant to that kind of electronic, but the one I've just mentioned, CRO, cathode ray oscilloscope, and the microelectronics, logic gate circuits. So that for that it will be valid, but not for the advanced silicon circuitry. So the first one is energy divided by time. P equals energy divided by time. P equals FD over T. P equals F times V. P equals I times A. P equals IV. P equals I squared R. P equals V squared over R. And then it's the rate of energy. It's defined as the rate of energy consumption, or the dot product of radiated intensity per unit area, and is used in electric, electronic, and thermal physics calculational analysis. And if we had a graph of energy versus time, where time is the independent variable, energy is the dependent variable, and we had, well, mostly we have the real life graphs are actually something like this. But if I were to draw an easy projection, a linear projection, so this is a linear projection. So the gradient would be so that'll be the gradient, and so that'll be power. Now average power will be power divided by under root over 2, sorry, under root 2, or half times P. But the for these you'll have to use integration and calculate power at different points, and then summate the power differential and summate the power values. So here you'll have to take a separate gradient. Here you'll have to take a separate gradient. Here you'll have to take a separate gradient, and it's getting a bit untidy now. So you'll have to take separate gradients at different humps and peaks, and so that'll define your acuity of